Good day, everybody. Today I'd like to talk about solving differential equations using Laplace transforms and really just bring in an analogy with using a table of logarithms, which is something that, thank goodness, we don't need to do anymore these days, but I think the analogy will still be helpful. So we'll take a look at it. The way using a table of logarithms would work is someone makes the table ahead of time and then we just have to use it, and that'll be similar with Laplace transforms. So here is a certain table. It's already been completed for us. So how would we use it? Well, I'll start with one of the easiest questions you could ask. What's 2 times 3? And so if we had to use our table of logarithms to solve that, you'd look up what natural log of 2 is. Actually, I should have said natural log. This will be log base 10. So I look up the log base 10 of 2, and that's 0.301. And we look up the log of 3, and that'll be 0.477. And since log A plus log B is log A times B, it turns out that if we add the two results we got, 0.301 and 0.477, well, we get 0.778. And now if I look for the inverse of that, you see here 0.778, its inverse is 6. So it must have been the case that 2 times 3 is 6. That seems pretty complicated. I mean, it's not worth learning how to use a table of logarithms to do something as easy as that. Maybe a slightly harder problem would be what's 2 times 3.42. So again, if I were to look in the table, log of 2, 0.301. Log of 3.42 is 0.534. If I add them up, I get 0.835. If I look in the table, that inverts to 6.84. So that's the result of 2 times 3.42. Again, it doesn't seem worth it to use a table of logarithms to do those problems, but this is just the beginning, and then gradually we do get to something that you cannot do with normal arithmetic and their operations. So let's see. I'll bring in one more tough example. This is going to be, so if you get to 2 times 5, if I were to look at my table here, 2 times 5, of course, is 10. And if you look up the logs, the log of 2 is still 0.301. The log of 5 is 0.699. They add up to 1, and the inverse log of 1 is 10. Notice there's lots of 1s there. We start to get rounding errors. And once you go beyond 1, then what we do is, well, I'll indicate it by this example. You separate the integer part and the fractional part. So I'm going to do 3.67 times 7.47. So if I look at the log of 3.67, that's 0.565. The log of 7.47, well, that's 0.873. If I add them up, I will get 1.438. So I have 1 plus 0.438. And you inverse log those answers, and then you can multiply them. So the inverse log of 1 is 10. Right? Log base 10 of 10 is 1. If I had a 2, inverse log of 2 would be 100, because log of 10 squared, log of 100 would be 2, and so on. So the integer part, when you inverse log, it will go 10 to the power. And then for the fractional part, you use this table. So this table will handle all the fractional parts, And then the integer part, we just went through how to handle. So the inverse log of the fractional part, 0.438, is, can't find it, 2.74. So now my final answer then is 10 times 2.74, which will be 27.4, which is accurate to the digits listed, but it's not fully accurate, but it is accurate to the 3 significant digits that I gave. So again, not easy, but let's keep going. You're not going to be tested on using a table of logarithms, but hopefully you'll catch on. Let's see here. If I want more accuracy, then they do have these 4-place common logs and with proportional parts. So for example, if I look at log of 2.0, which is right over here, they don't have the decimal point, but I mean, you can read it in different ways. We're going to read it as 2.0, and so that gives me, and then if I go one column over, the natural log of 2.00 would be 0.3010. And then if I go to the next column, the log of 2.01 is 0.3032. And then for numbers in between 2.00 and 2.01, you expect the log to be in between there, and this proportional part kind of tells you how much. So for example, the log of 2.004, that's in between the two. You look in the column with the 4, I have to add in 8 to that last decimal. So the log of 2.004 is going to be 0.3018 by using the proportional parts. Now, most of the time, the proportional parts is going to be a single digit, but it can be a double digit. Like, well, if I go all the way to the end, log of 2.009, now I'm almost at 2.01. I have to add 19 to that last digit, but that's like, so that creeps over, and you end up adding 0.3010 and 0.0019 to get 0.3029, which is just short of the 0.3032 that if I were to bump it up ever so slightly, you'd get to log of 2.01 is 0.3032. So that's using proportional parts. Maybe one more multiplication here. I think this will fit here. If I were to multiply 3.674 times 7.465, then the log of 3.674 is 0.5647 plus the proportional part of 0.0005 will give me 0.5652. Whew. And log base 10 of 7.465 is going to be 0.827. Proportional part will give me 0.0003. So that adds up to 0.8730. And now if I add those two values up, 0.5652 plus 0.8730, I'm getting 1.4382. So I have to invert the 1, that'll just be 10, and then multiply that by the inverse of 0.4382. So we have to use the table as best we can. Inverse log of 0.4382 is 2.74, and I'll say 25, because 4 is midway between the 3 and the 5 in the proportional parts column. So I added 0.004. So that gives me, as I said, 2.7425. So my answer for the multiplication is 10 times 2.7425, or 27.425. Not easy to say when I can't write it down. But that answer is accurate to within 0.0015. So, I mean, it's pretty accurate. So, now for the grand finale of the table of logarithms. I want to compute and take a quick peek at my little work here. 5.83 to the power 4.62. So that I don't think I can find any good way to do, without, I mean, obviously with calculators, but say, you're in the 1700s. How are you going to do that? You can't really raise numbers to those difficult fractional powers. If you think about it, I'll let you think about that on your own time. But anyways, by using a table, well, we do have to use the property of logarithms. So what I'm going to do is take the log of the answer, or I'm sorry, the log of the question, and then we're going to work in the transform side. That's the whole point. So we're going to then work in the transform side, I'm going to call it, because we're going to Laplace transforms. Do some math there, and then invert, transform our answer to get the true answer. So if I take the log of 5.83 to the 4.62, that power can come out front. It'll be 4.62 times the log of 5.83. The log of 5.83, you can see, is 0.7657. So now I just need to multiply 4.62 times that number, and I get 3.537534. So using this table I have here, I can find the inverse of 3.5375. Inverse of 3 will be 10 cubed. The inverse of 0.5375 is going to be 3.447. So 1,000 times 3.447 is 3,447. So that would be our answer to the problem. And it's extremely close. It's really good. If you had more places in your log table, you'd have more accuracy. But you can try and find another way to do it by hand. And good luck with that. And so again, that's the analogy with Laplace transforms. We'll start with some problems that we can easily do through other methods. And that's just to get the warm up. And gradually we go to problems that you would not want to do with the other methods that we already know. So first I'll look at the table. Here's the definition. We're not going to use that, so you have to make the table, but once the table is made, you don't have to use the definition anymore. So this is a small list of some transforms. So we have on the left our function, which sometimes we can call f, and then we transform it, we call it big F, and then there's a new variable f of s. Other times I like to think of it for the differential equations, little y of t, and then the transform would be big Y of t. So we think both ways. And we're going to take the transform of the left side to get the right side. But we also want to inverse transform the right side to get the left side. So we think of the left side also as the inverse transform of the right side, because we're going to do both. We're going to take a transform, we're going to invert a transform. So here's a little list. So there we go. But the ones we need, I'll put as I need them. So let's see here. So again, starting with the analogy, there's a difficult problem. This would be one way you could try and do it, but you wouldn't want to do it that way. And even if you wanted to approximate, it's close to 4.6, which would be 23 over 5, but even this number to the 23/5 wouldn't be a great way to get accuracy. So that's the analogy. For Laplace transforms, again, what we're going to do, we're going to have a differential equation with y, we often say is in our t domain, and then we take the transform of both sides. So we have an equation, and then we're going to get this y of s in the s domain, solve for y of s, and that only requires algebra once the table's been made. And then if you invert the transform, you get your solution. So, first example, just to see what's going on. We'll solve y double prime plus 4y equals 0 with initial conditions. Y of 0 is 3, y prime of 0 is -5. Easily solvable, but let's do it with transforms. So we take the Laplace transform of both sides. A few things we need to learn, like in essence, what a mathematician would say is it's a linear operator, and that would always mean, so the Laplace transform of 0 is 0. You can see that from the definition, or that it's because it's a linear operator. But so the Laplace transform of sum will be the sum of the transforms, and constants will factor out. And then by definition, the Laplace transform of y is just big Y. And then from the table, the Laplace transform of the second derivative is given by s squared, Laplace transform of y, minus s times y of 0 minus y prime of 0. So I'm going to just write big Y instead of y of s. So I have s squared y, and then minus s times my initial condition, y of 0 is 3. See it right there. And then minus y prime of 0 will be minus a -5. So now I want to solve for big Y. So I'll move these two terms over. So that's minus 3s, move it over, plus 3s, minus 5. Well, plus 5, move it over, minus 5. These two terms each have a y. So I can factor y out from 4 plus s squared, solve for y. There it is. Now to invert the transform, we'll use our table. If I was taking a transform of cosine or sine, I would get essentially these type of terms. And so the inverse of these type of terms give me back a sine and cosine. I just have to have it in the right form. Cosine's a little bit easier. You just need an s on top. And so this 3 you can think of putting out front. For sine, I've got this s squared plus a squared. I need an a on top. So this is s squared plus 2 squared, so I need a 2 on top. So you put a 2 there, you divide by 2. And then when you invert the transform, this is what we get. And so that solves our differential equation. Again, done a little quickly. But it's just to show you what's going to happen. Maybe a couple more examples. Here's another differential equation. Again, homogeneous. We're going to solve by using Laplace transforms. We have initial conditions. Y of 0 is 2, and y prime of 0 is -1. So the Laplace transform of the left will be the Laplace transform of the right, and that will be 0 on the right. For the left, it's a sum. Laplace transform of a sum is the sum of the transforms. Constants factor out. By definition, Laplace transform of little y is big Y. And then we see from the table, Laplace transform of y prime is s times big Y minus y of 0. And Laplace transform of the second derivative is s squared big Y minus s times y of 0 minus y prime of 0. So that's all done there. If we simplify, and I don't now only write big Y instead of y of s. And we want to solve for big Y. So the terms without the Y, we move to the right. So we have a minus 2s, we have a plus 1, and a minus 6. So it's 2s plus 5 here. On the right-hand side, we've got this quadratic, which would have been our characteristic equation if we had done it through our other way. But now we're solving for big Y. So if I divide, we get this. And you won't find this in the table. Turns out what we need to do is use partial fractions to break it up. Yeah, so it's only algebra that we need to use, but it's not trivial algebra. So to use the table, I'll break this fraction into a sum of two fractions this way. And I'm not going to go through the work. Hopefully you've seen some partial fractions before, but in the end, you get big Y is this fraction plus that fraction. So now they're nice and simple. And now we can invert using our table. And you can see A is negative 4 for the first fraction. So I get 3/5 e to the negative 4t. A is 1 for this one, so I'll get 7/5 e to the 1t. And that would be the answer. So again, it solves the differential equation, and it's got the initial conditions, right? If I plug in 0, you get 10/5, which is 2. If you take the derivative, I'll get negative 12 plus 7 is negative 5 all over 5, so that'll be negative 1. So it's going to match my initial conditions. It would solve the differential equation. Last example, non-homogeneous one. But again, a little simple left-hand side here. So y double prime plus 25y equals 20t. Y of 0 is 3. Y prime of 0 is 5. Let's take the Laplace transform of both sides. So again, Laplace transform of 25y will just be 25 big Y. And the Laplace transform of the second derivative is s squared big Y minus s times y of 0, so minus 3s, and minus y prime of 0, so minus 2. So I need to solve for big Y. So got two terms with the big Y. These two terms I'll move over and divide. And now I need to use partial fractions again, not for this part. So this part I can split up easily enough. But this one I need partial fractions, and again I'm going to skip those details. But in the end we get big Y is 4/5 times 1 over s squared. Look at my coefficients here. I think I can get them all to fit. Minus 4/5 s squared divided by s squared plus 25. So that was just from this. And then this fraction I didn't do anything with, but I'll split it into 2. It's split into 2 like before over here. So I've got the 3 times s is right here. 2 divided by s squared plus 25. Well, I need an a on top, so I put a 5 on top, divide by 5. So this will invert to 2/5 sine of 5t, and this one will invert to a 3 cosine of 5t. The 4/5, if I bring it out, well, I need a 5 on top, so divide by 5. That makes minus 4 over 25 right here, and then this will invert to a sine of 5t. So I have two sines, and I'll combine them. Well, I did it right there. And then the 1 over s squared converts to just a t. So I get 4/5 t. So there's the differential equation. It's a pretty simple one again. It takes a while. If you do enough Laplace transforms, then it gets easier to do the harder ones. And then gradually you can also do the ones that have a more convoluted right-hand side. Most of the time for our right-hand side, it'll just be kind of a piecewise change is what we're going to go after. and also some impulse Dirac delta stuff. All right, so I will leave it at that and hope this helped.